Energy stored in a capacitor. Let a charge Q is transferred from one plate to another plate of the capacitor. Then the potential difference V between the plates is given as V is equal to Q over C. Let an extra charge dQ is transferred between the plates of the capacitor. Then the work done will be given as dW is equal to V times dQ. Now let's substitute the value of V is equal to Q over C over here. And if we do that, we will write dW is equal to Q over C dQ. Now let's find the total work done to charge the capacitor with a charge Q is given as W is equal to integration of dW, and if we substitute the value, we will write W is equal to integration from 0 to Q over C dQ, because we are charging the capacitor from 0 because there is no charge on the capacitor, and the capacitor is charged all the way to small q. If we simplify further, we will take 1 over C out because 1 over C is a constant, and we will write W is equal to 1 over C integration from 0 to Q dQ. Now let's integrate, and if we do that, we have W is equal to 1 over C Q square over 2 lower limit from 0 to upper limit Q. Now let's substitute the value of lower limit and upper limit, and if we do that, we will get W is equal to 1 over C inside the bracket Q square over 2 minus 0. Let's simplify further, and if we do that, we will get W is equal to Q square over 2C. Now we know that the work done is stored as the potential energy U in the capacitor, so we have U is equal to Q square over 2C because this work is basically a potential energy. So U is equal to Q square over 2C, and this is our equation number 1. We know that Q is equal to CV, and let's substitute that value in the equation number 1, which is U is equal to CV because this is Q squared, so CV squared over 2C. If we simplify further, we have U is equal to C square V square over 2C. We can cancel 1C out, and if we do that, we will get U is equal to 1 over 2 CV square. And this is our equation number 2. Now let's simplify further, and if we do that, we can write U is equal to 1 over 2 C V times V, because V square can be written as V times V. And if we do that, we have this expression, which is U is equal to 1 over 2 CV times V, and we know that CV is equal to Q from here, and if we write that, we have U is equal to 1 over 2 QV, and this is our equation number 3. So basically we have 3 equations for the energy stored in the capacitor. So if we combine equation 1, 2 and 3, we have U is equal to Q square over 2C, and that is equal to 1 over 2 CV square, and that is equal to 1 over 2 QV. So basically we have 3 equations, and depending on what is given in the expression or in the equation or in the problem, we can use one of these 3 equations to find the energy stored in the capacitor. And this is how we'll define how to find energy stored in a capacitor.